Black holes are probably among the most mysterious and fascinating objects in the universe, and they represent one of the most surprising predictions of Einstein's theory of relativity. However, the same theory suggests the existence of something just as strange, if not even more enigmatic: white holes. But what are white holes? Could they really exist? And do they have any connection with the Big Bang? Let's try to find out. Many of us have heard of black holes. For those unfamiliar with the concept or those who want a quick refresher, here are the main points. Einstein's general theory of relativity describes gravity as a manifestation of the curvature of spacetime, also providing us with the mathematical tools to calculate the geometry of spacetime around a mass. One of the simplest solutions to general relativity was found by the mathematician Karl Schwarzschild in 1916. This solution describes the geometry of spacetime around a point mass, that is, a mass concentrated at a single point in space. A peculiar feature of Schwarzschild's geometry is the event horizon, a spherical surface that can only be crossed in one direction. You can only enter, but never exit. Not even light can escape within the event horizon, making it a completely dark sphere, or in other words, a black hole. At the center of the Schwarzschild solution, where all the mass is concentrated, the density and the curvature of spacetime become infinite, forming what in physics is called a singularity. Once the event horizon is crossed, there is no way back, and the fate of anything that passes it is to inevitably fall toward the singularity. This is the summary. According to the solution of general relativity, you can only cross the horizon of a black hole from the past to the future, and once crossed, you will always move toward the singularity, just as you inexorably move forward in time. It's a process that follows a precise and irreversible direction. However, this seems to contradict a fundamental principle of physics: time symmetry. The equations of physics are generally time symmetric, meaning they can be read in both temporal directions. So, there might be a suspicion that the solution describing a black hole is incomplete and that there is a missing part that restores this time symmetry. By analyzing Schwarzschild's geometry more closely, it turns out that there is indeed a time-symmetric solution to that of the black hole. This solution is a sort of time inversion of the black hole and is called a white hole. But what does a white hole look like? If a black hole has a spherical horizon that can only be crossed in one direction, entry, a white hole has a horizon that can only be exited, but not entered. This horizon spits out matter and radiation, making it bright, in stark contrast to a black hole, which appears black. Moreover, while in a black hole the singularity lies in the future and cannot be avoided once the horizon is crossed, in the case of the white hole, the singularity is always in the past, so it can never be reached. It's as if the matter comes from the singularity but can never return to it. From the point of view of an external observer, an object approaching the horizon of a black hole seems to take an infinite amount of time to cross it, making it impossible to observe the passage. Conversely, light coming from the horizon of a white hole takes an infinite amount of time to reach an external observer, making the white hole equally unobservable. So, from a mathematical point of view, we have defined what a white hole is. But do they really exist? The first thing to say is that the Schwarzschild metric is an idealization that describes spacetime around a point mass, meaning a mass concentrated at a dimensionless point with infinite density, i.e., a singularity. We know that black holes can really form because there is a real physical mechanism, namely the collapse of stars, which leads to the formation of a black hole. The evidence for the existence of black holes is numerous and well documented. However, there is no analogous process that could form a white hole in our universe. The idealized Schwarzschild solution, which is time-symmetric, describes an eternal situation. One part of the solution is a white hole that has always existed in the past, and the other part is a black hole that will exist forever in the future. But our universe has a finite age, so eternal objects cannot exist. Another reason why the existence of white holes is doubtful is that their formation would go against the arrow of time, violating the second law of thermodynamics. In the real world, spontaneous processes always occur in the direction in which entropy increases, making the formation of a white hole incredibly improbable, to the point of being considered impossible. When talking about white holes, we venture into the realm of theoretical speculations. Some quantum gravity studies hypothesize that white holes could form from black holes, but these ideas are still very speculative. However, there is a phenomenon that could resemble a white hole, the Big Bang itself. If we look at the simplest description of the Big Bang, we see a singularity in the past from which matter and radiation emerge. It cannot be ruled out that the origin of our universe is related to a white hole or that the collapse of a black hole could give rise to another universe. In conclusion, black holes, strange as they may seem, are a confirmed reality. White holes, on the other hand, remain a fascinating and hypothetical mystery, with no concrete evidence of their existence and many doubts about the possibility that they could exist. Thank you for watching, and don't forget to subscribe to the channel and hit the bell to not miss the next videos.